We'll go a little bit more in depth into work. So the way we introduce work initially was we say we take an object, maybe 3 kilogram object, we do a 6 Newton force on it, make that distance something like I don't know, 4 meters. We can easily calculate how fast this is going. We'll start it from rest. Work energy theorem would say there's our starting kinetic energy. We're going to add that much energy in this particular case, and we're going to get a new kinetic energy here. So it's a pretty easy calculation because that's 0. This would just be the force times the distance. I'm not even going to write the cosine theta because they're parallel. And then that would give us our final kinetic energy, 1/2 mvf squared. So that would be 6 times 40, or excuse me, 6 times 4, which is 24 newtons. And then when we do 24 equals 1/2 times 3 times vf squared, we would get a final velocity of 4 meters per second in the end. So clearly this object has gained kinetic energy. Now we do want to actually talk about the theta aspect if your force is done at an angle. Alright, so if we do this and we take that same force, the 6 newtons, and apply that over the distance of 4 meters, same force, or at least same size of the force, same distance, but now there's an angle between them. We'll make it like a 30-degree angle. We've already seen what happens when we try to drag something at an angle. It'll still move horizontally. Now we could break this down into a component, a parallel, and a perpendicular component. And what you're going to see is that the parallel component will do the work. The perpendicular component will do no work because one has an angle of 0, one has an angle of 90, or we could just write it in as FD cosine theta. So the work energy theorem is going to look identical here. But when we look at the resulting scenario, we'll start it from rest again. Starting kinetic energy 0, but now we have FD cosine theta, where theta is 30, and this would be 1/2 mvf squared. So that's going to be 6 times 4 times cosine 30 equals 1/2 times 3 times vf squared. So 6 times 4 times cosine 30 gives us 20.78 joules. Now, that's important because what that has just shown us is that by applying this same force but at an angle, we don't add as much energy to the system. Our object is not going to be moving as fast. So when we calculate VF based off of these numbers here, I'm only going to get 3.72 meters per second. So applying it at an angle means that not all that 6 is parallel, and then in this particular case it added less kinetic energy to the system that we're looking at. Now it's also possible to have multiple forces doing work simultaneously. To give you an example of that, let's say that we've got something that, again, we'll start it from rest. Might as well make it 3 kilograms. Let's do a 6 Newton force that way. Let's do a 2 Newton force that way. And we'll do that over 4 meters. That's a force of kinetic friction. All right, so what we're doing is we are dragging this object one way. Friction's working against us. This is going to do positive work. This is going to do negative work because that's a force that's to the left. So you got two things working against each other here. And essentially what we want to do is represent that with the work energy theorem. Now there's two ways to do that. You could either say, all right, we're going to use a single value for work by calculating the work done by this, and then basically we might call this the net work or the total work. That's an option. You can also say, all right, well, we'll have a work term for each of these forces here. So I could have a work from the applied force of 6 newtons and a work from the force of kinetic friction as well. Two separate things doing the work, and they're both going to change the energy. And it's still going to give us a final kinetic energy. So when we're looking here, starting kinetic energy 0, the applied force is 6 over 4 newtons. That applied force adds 24 newtons of energy to our object. But then when you look at the force of kinetic friction, which is pointed in the opposite direction, -2 times 4, that's going to remove 8 newtons from it. So then we have 1/2 times 3 times VF squared. We'll solve for VF again here. So we got 2 terms here now. And when I account for them both, we're only going to get a VF of 3.26 meters per second. So we get less than the initial case where there was no friction at all. So you can have something adding energy to it while something else is simultaneously removing energy. The thing I also would have to point out here is that both of these I would treat as an angle 0 because they are parallel to this vector as well. So probably last thing we want to cover with respect to, work energy theorem is maybe just looking at something that just removes energy exclusively. So when we've done problems like this where we've maybe have something moving and we say, okay, well, what it's going to do is it's working against this rough surface here. There's going to be friction all along the way. And we could say, well, how long did it take for it to stop? Maybe there's a force of kinetic friction that way. We can say that the mu k value of the surface, we'll do 0.2. Let's stay with the theme of a 3 kilogram object here. We have a way to solve for this. In fact, when we did the forces approach, we got the rate of deceleration, and we actually proved that it was independent of mass. Let's look at it from a work energy standpoint. We don't know how far this is. Maybe that's what we'll figure out here. I do know it's kinetic energy here. We know it's kinetic energy here. So what we have is a starting kinetic energy of something that's fairly significant. Friction is going to do work all along the way. In this case, it's going to remove energy. And then we're going to have a final kinetic energy that happens to be 0 here. So let's call this 1/2 mvi squared. Let's call this negative fk because it's pointed to the left times d. And then let's call this 0 because it's going to be at rest here. Why don't we move that over to there so it's positive? So we got fkd over here. And then what we can do is we can say, all right, well, we know this is on a level surface, so this would be mu k n times d. But n on a level surface is equal to the force of gravity, so the last step would be mu k mgd. And then what you see is that, again, we've proven through energy that this process is independent of mass. And now putting our numbers in, we have 3 here, we have 0.2 here, 9.81. The only unknown is d, so I can put in our numbers. Excuse me, I said 3, that's a 5 actually. So 1/2 times 5 squared would equal 0.2 times 9.81 times the distance. And when I solve for d, if I've done it properly, I'm getting a d value of about 6.37 meters. And if that is correct, I would expect to get that regardless of the approach I took. I could do it from this approach, or I could use forces in combination with kinematics. Last thing with respect to work. All the forces that I've given you have been a set value where they don't change. It is possible to increase or decrease forces as you're applying them. So, in all the cases, if we were plotting a graph of F versus D, we were dealing with a case where the forces just don't change at all. But we could have a scenario where the force grows as you move along, or as the object is moving along. We could have a scenario where possibly the force is already something and it shrinks. We can even have it where it does all kinds of stuff. Maybe something that grows, stays constant, and shrinks. There's a lot of different possibilities here. But for this is the one where the formula would apply here. And let's actually not even think about cosine theta. Let's talk about things that are just, parallel here. Multiplying f times d makes sense here. But what we're inadvertently doing is we're getting the area between that curve when we do that. We're multiplying this force by this distance here. If our force is variable, we don't have the option of using a formula, but we can easily get our work by taking the area between these curves here. And the area would represent the work in joules. In fact, the units work out just that way. You'd still get kilograms meters squared per second squared. And keep in mind, it's entirely possible for your force also to be negative, while your distance might be positive, or your displacement. So you might get a negative value of work as well through this graphical technique. So when we have variable forces and we're presented the information through graph, we can get our work that way as well.